So thank you for your nice introduction. Before I move to our own implementation, let me just show you a conventional readout chain for stress sensors. And at the very beginning of our readout chain, we have our sensor itself. And there are several options to implement a sensor. That might be a resistor, that might be a transistor. You can also implement a stress-sensitive current source. So things we have to consider at the sensor itself is, first of all, noise. We want to have a high SNR, and it's mostly defined by the sensor. Second, there's power, if you think about IoT nodes, for example. And third, area, because we want to have a high spatial resolution. So the problem is with the sensor itself that the signals are quite small. So we're dealing with signals in a range of microvolts to millivolts, so we need certain amplification. And in order to do so, that amplifier has to preserve signal integrity. Furthermore, it's noise, power, and area critical. Since we're dealing with noisy signals, we should place a filter in order to, first of all, limit the thermal noise floor, and second, prevent anti-aliasing, or prevent aliasing in the subsequent AD conversion. And depending on the cutoff frequency, that one is area critical. So the last part of the signal chain is our ADC, where we perform the quantization and sampling. So that one is power critical because we don't want to waste all the effort we spend in the preceding blocks. So there's one thing I haven't mentioned so far, and this is a long wire. So imagine your sensor is somewhere over here, while your reader electronic is at the bottom of your chip. So this is a long wire which is prone to noise pickup or interference. If you think about sensor arrays, there's something else which comes into play, and this is probably a parasitic bus. So imagine you're multiplexing multiple sensors onto an analog bus. This is adding a huge capacitance, and together with the sensor output impedance, somewhat determines the settling time of our system, and therefore the conversion speed. So the question is, can we get maybe rid of the filter, maybe also rid of the amplifier, and maybe of the multiplexer? And this is where direct digitization comes into place. So what we're having, we're keeping the sensor itself, but replacing all the other components by means of a continuous time delta sigma ADC. So things we have to consider is, first of all, signal integrity, and also noise, power, and area, but this time it's all concentrated in one building block. So some benefits that come with that implementation is intrinsic filtering, and we don't need any preamplification because the amplifier, or the ADC is designed for small input signals. What else? We can reduce the area and power. We can thereby place the ADC closer to the sensor itself. We don't have any long analog routing, therefore less capacitance, and we're actually faster. The question is, can we get even further and implement our sensors or embed them into the ADC? So this is what you can see over here. So if you multiply the building block several times and have a capable interface, we'll end up with the approach I'm showing you in the next few slides. So let me start with the sensing element itself. So what we are using are semiconductor-based stress sensors, which rely on the redistribution of electrons in holes and also on the curvature of valence or conduction band. The sensor itself is somewhat anisotropic, but if you arrange the transistors in a correct way, which I will show you now, we can definitely sense stress signals. So what do we actually sense? Well, it's the modulation of mobility with the stress itself. The effect itself is quite sensitive, but comes at a drawback of a strong temperature dependency. So if you're interested in sensing normal stress differences, you would arrange your transistors in that shape, so going for 0 and 90 degrees, whereas you're interested in shear stress, you would arrange your transistors in minus 45 and 45 degrees angles. So I just want to mention that you only actually need 2 sensors, but 4 are better for matching. So if you go through these equations, which can be simplified, so if you assume that the common mode stress is rather small, and that's definitely valid in the range of, let's say, 100 to 200 megapascal, we can simplify to just a pi coefficient for every sensor type times the input stress. So next step is to get at least some signal amplification. Like I told you, the signals are in general quite small. And so let's have a first look at a general voltage-based amplifier. So there's going to be a voltage at the input, and it's going to be seen amplified at the output. The question is, what happens if there's stress on your input transistor? And the thing is, nothing's going to happen because it's rejected by the common mode rejection of your amplifier. So the situation is somewhat different if you mess up with the layout either on purpose or by mistake. And this is what you can see over here. So I replace these two input transistors with the sensors itself and applied a constant voltage at the gate. So if that voltage is changing, you don't see anything at the output, but if stress is acting on these transistors, we have a corresponding current or voltage at the output. So in the next step, we're going to improve that amplifier a little bit and create a so-called strain-sensitive GMC integrator. So what you can see over here is we kept the tail current source here at the top and have our two sensors for shear and normal stress differences. So the second part is a switch matrix, which allows us to switch in between the two readout modes, and it's also used for the adjacent AD conversion, which I'll show you in a minute. There's several building blocks which are shared for both results. So first of all, we have the output stage, and second, there's the feedback currents we need for the subsequent AD conversion. So you're probably asking why I'm showing an integrator, and the reason is simple, because the integrator is the loop filter of our delta sigma or continuous time delta sigma two-step ADC. So as you can see over here, we have the strain-sensitive GMC integrator, which is actually converting our stress signal into a current. And the current is integrated on the integration capacitor over here. And the voltage is then compared to reference. And depending whether we are larger or smaller than 0, the quantizer itself is going to make a decision. And depending on that decision, we apply some feedback pulses. In that case, it's a current feedback, which is controlling our current signal to 0. There's a second feedback current source here at the bottom, and that is used for the so-called two-step implementation I'll show you in the next slide. What are the benefits of using continuous time two-step incremental delta sigma? Well, first of all, we have an integrated low-pass transfer function, which we call the signal transfer function as shown over here. Reconstruction is pretty simple. You just need a counter, at least for that implementation. And we can reuse several building blocks for the conversion, namely the integrator and the comparator. And last but not least, it's multiplexable. That's the reason why we can switch in between shear and normal stress differences. So let me explain you now the two-step conversion principle. In the first phase, which is called the delta sigma phase, we're going to connect our input transistors differentially and convert that stress-dependent current by means of I feedback 2. So this is a classical delta sigma conversion. In the second step, after 127 cycles, we move on to the so-called counting phase. And during that phase, we're going to cross-couple the inner two transistors, thereby effectively nullifying the input signal. However, the signal itself is still stored on our integration capacitor. Or what we do now is we use a second feedback current, the I feedback 2, and count the cycles we need to discharge the capacitor. In the last step, we're going to reset our modulator, switch on to the next stage, so from shear to normal or vice versa, and then we can finally obtain our conversion results. So what is nice about that implementation is that it's more or less the same performance you get for a second order modulator at the hardware expense of a first order modulator. So this is why we're doing all the effort. So if you take now several of these building blocks, you end up with the system we implemented. So it's a needle-shaped array. We have 96 sensors, which are arranged in 48 recording sites, which all have a shear and normal stress readout. So the interface itself for a sensor can be interfaced via a bidirectional two-wire interface, where we have serial data and configuration chains. If you talk about the sensors itself, we realized a parallel readout, so this is important to state, which allows us to convert every sensor at a bandwidth of 20 kilohertz. Full-scale values for shear stress is 330 megapascal, whereas we have 161 megapascal for normal stress differences, and all at a resolution of 11-bit. So let me show you now a chip micrograph of the array we implemented. So it has 5 millimeters in length, with a width of about 110 micrometers. So if you zoom in one of the unit cells, we can see that roughly 60% is consumed by digital, whereas we have the analog blocks I've shown you before, somewhere over here, and especially these two sensors. So I think you remember these from one of the previous slides. So shear stress sensor and normal stress sensor. So what we actually try to do is we try to evaluate our system, and in order to do so, we bonded our sensor reticle on top of a PCB. and place that PCB into a so-called 4-point bending bridge. The nice thing about the 4-point bending is that you have a constant stress profile within the inner 2 loading pins, and therefore it's nice to evaluate the linearity of our sensor. And as you can see over here, the linearity for both sensor types, shear and normal stress, is quite nice. So the R-square value is always greater than 0.99, and also the gain distribution across the sensors is quite tight for a normal stress sensor. It's a little bit widened for shear stress sensors. However, we assumed it's due to geometry because the reticle itself is not quadratic, but rather rectangular. In a second step, and I said before, we want to go for high-speed sensing, we excited our PCB with an electrodynamical shaker and recorded the response. There were two frequencies, one with 1.3 kilohertz and a second one with 10 kilohertz, and this is the response we measured. I have to admit, like, the response is quite small. We're far off the resonance frequency of our circuit. Therefore, it was just a proof of concept that we're able to sense such high-frequency signals. But anyway, we were able to. And the last thing we tried to figure out was the spatial resolution of our system. And therefore, we glued our reticle on top of a flex PCB and put it in a custom micro bending bridge and applied a triangular stress distribution. And as you can see over here, the results look quite promising. So we have the triangular shape. There's a little bit deviation here at the top, so this is probably because I didn't hit a sensor directly, but rather in between two sensors. And also there's a non-zero shear stress component, which is probably because it's really hard to align the reticle in that setup. So let me conclude now with a state-of-the-art comparison. And I have to admit, it's really hard to compare these implementations because every implementation has a different target. But let me try it anyway. So what we did is we implemented 96 sensors, which is 3 times more than previous implementations. If we break it down the area to area per sensor, we could improve by more than a factor of 10 compared to previous implementations. However, we can't really sense the actual stress direction, but rather in-plane and shear stress. Also, if we talk about resolution, we can compete with others because our system is basically designed for high-speed sensing and not for super precise sensing. And, well, this is what I mentioned. We're fast. We're definitely faster, about 50 times faster than that publication, probably also more than a factor of 2 faster than that publication. And this is due to the parallel nature or parallel conversion of all our sensors. If you break down the power to power per sensor, we could improve by a factor of 2. So with that, let me conclude my talk. So we presented a 2 times 48 sensor needle-shaped array, which is meant for height bandwidth sensing, which could define the state of the art in terms of density, power, and bandwidth. Thank you very much. I'm open for questions.